Welcome to our session on the Blueprint for Enterprise AI on Azure. Today, we will explore the comprehensive lifecycle journey required to move from initial code development to a fully realized multi-tenant cloud-native application. We will examine the essential components of this architectural framework, including development workflows, container orchestration, and the seamless integration of artificial intelligence within the Azure ecosystem. This guide provides the strategic roadmap necessary for organizations to successfully deploy and manage sophisticated AI solutions at scale. Welcome to an overview of the complete architectural blueprint for a modern, cloud-native application ecosystem on Azure. This design integrates several critical layers to ensure security, scalability, and intelligence. At the entry point, we have Azure DevOps, which manages both the CI/CD pipeline flow and the command path. This forms the CI/CD supply chain, where code is transformed into containerized workloads and stored within the Azure Container Registry. The entire environment is secured within the network foundation, defined by the Azure Virtual Network. This isolation ensures that traffic between services remains private and protected. Central to the architecture is the Kubernetes Compute Hub, powered by an Azure Kubernetes Service Cluster. This is where our containerized applications are deployed and managed at scale. Finally, we look at the intelligence and persistence layer. Here, Azure AI Foundry provides advanced cognitive capabilities, while Azure Storage handles data persistence. This integrated approach ensures that the Compute Hub can seamlessly interact with AI services and storage resources to deliver a robust and intelligent end-user experience. Welcome to this overview of building a secured virtual network, which serves as the fundamental architecture for a modern cloud environment. As you can see, the Azure Virtual Network, or VNet, acts as the logical boundary for all traffic, ensuring that all internal communication is fully contained within the secure perimeter. Starting on the left, our process begins with Azure DevOps. From here, we establish a robust CI/CD supply chain. The pipeline flow pushes container images into the Azure Container Registry, while a dedicated command path allows for secure management of our resources. At the heart of this architecture lies the Azure Kubernetes Service Cluster, which we refer to as the Kubernetes Compute Hub. To maintain high security standards, we utilize subnet segmentation. This provides dedicated lanes for AKS nodes, private endpoints, and ingress traffic, preventing overlap and enhancing control. Above the Compute Hub, we have the intelligence and persistence layer. This includes Azure AI Foundry for our intelligent workloads and Azure Storage for data persistence. Crucially, all traffic between these PaaS services and our Compute Hub travels over private links. This means communication stays entirely on the Azure backbone and never touches the public internet. Finally, it is important to note our networking model. We utilize Azure CNI to achieve production-grade performance and seamless integration across the entire environment. This comprehensive approach ensures that our infrastructure is not only scalable and intelligent, but most importantly, secured by design. Welcome to step 1 of our journey, the supply chain from code to container. This stage is critical for ensuring a secure and efficient transition from development to deployment. The process begins with Azure DevOps, which hosts our application source code and manages the CI/CD pipelines. As code changes are committed, the CI/CD pipeline flow initiates. A vital component here is the Secure Service Connection, which authorizes Azure DevOps to build the Docker image and push it directly into the Azure Container Registry. The Azure Container Registry, or ACR, serves as our private and secure repository for all container images. It is nested within our network foundation, governed by the Azure Virtual Network to ensure that our assets remain protected. Moving into the core of the infrastructure, we have the Kubernetes Compute Hub, powered by the Azure Kubernetes Service Cluster. This hub pulls the authenticated images from the registry to run our applications. Supporting this compute layer is what we call the intelligence and persistence layer, which includes Azure AI Foundry for advanced model integration and Azure Storage for reliable data persistence. This entire ecosystem is designed to move your code from a repository into a production-ready containerized environment with security and scalability at every step. Step 2 describes the deployment phase and the critical handoff to Kubernetes. Azure DevOps, or ADO, uses a Kubernetes service connection, authenticated via a service principal or managed identity, to execute deployment commands. During this process, commands like kubectl apply or helm upgrade are run against the target AKS cluster. These deployments are precisely targeted to a specific line of business namespace, such as Lob Finance. The architecture leverages a virtual network to connect ADO with the Azure Container Registry, Azure AI Foundry, and Azure Storage, ensuring a secure and streamlined deployment to the AKS environment. In Step 3, we examine the runtime environment and how images are pulled securely. The process begins when AKS initiates an image pull after a new deployment is detected. This pull request travels via the VNet's private endpoint for ACR, ensuring the traffic remains off the public internet. Authentication is handled by the kubelet's managed identity, which is granted the ACR pull permission on the registry, so no static credentials are needed. This provides a secure and automated path for images stored in ACR to reach AKS, integrated within a broader workflow involving Azure DevOps, Azure AI Foundry, and Azure Storage. In Step 4, we examine the runtime phase, where the application actively calls for intelligence. At this stage, the application is deployed and running with an Azure Kubernetes Service, or AKS. To leverage advanced capabilities, the application makes a REST API call to an AI model, such as GPT-4o, hosted in Azure AI Foundry. To ensure this communication is secure and streamlined, we utilize Azure Workload Identity. This allows the Kubernetes pod to assume a managed identity, which is then used to authenticate directly to Azure AI Foundry. The primary benefit of this architecture is that it enables entirely keyless and secretless API calls, significantly enhancing our security posture by removing the need to manage or rotate traditional connection secrets. Step 5 of our runtime architecture focuses on persisting state, a critical component for ensuring data longevity in a containerized environment. While containers are ephemeral by nature, our applications require a reliable way to store and retrieve information, such as system logs or user-generated files. As we look at the workflow, Azure DevOps coordinates the integration with Azure AI Foundry and manages the delivery of container images to the Azure Container Registry. These images are then pulled into the Azure Kubernetes Service Cluster through a secure private endpoint. To handle data persistence within the AKS cluster, applications mount persistent volumes. The orchestration of this storage is handled by the AKS Container Storage Interface, or CSI driver. This driver is responsible for dynamically provisioning the underlying Azure managed disks, or Azure files, that provide the actual storage capacity. Finally, it is important to note that all communication between the AKS cluster and Azure Storage is routed through a secure virtual network. This ensures that the data traffic remains private and adheres to the same security standards applied across the rest of the infrastructure. The application lifecycle journey is complete. We can now see how a single piece of code evolves into a running, intelligent, and persistent application. The process begins with Azure DevOps for source control and CI/CD, feeding into the Azure Container Registry. By leveraging a private endpoint, we ensure that the entire workflow remains within a secure private network boundary. The application is hosted on Azure Kubernetes Service, where it draws intelligence from Azure AI Foundry and achieves data persistence through Azure Storage. While we have established a secure and functional end-to-end pipeline, the next challenge is to consider how this architecture scales to meet the demands of an entire enterprise. As we transition our strategy from managing a single application to building a robust multi-tenant platform, we face a significant architectural shift. This pivot centers on leveraging a shared Azure Kubernetes service cluster. While this approach is highly cost-effective, it presents 3 critical challenges that we must address. First is isolation. We need to ensure that different lines of business operating within the same cluster do not interfere with one another. Second is security. We must implement strict controls so that teams can only access their own specific applications. Third is fairness. We have to prevent any single line of business from monopolizing with shared resources. Our goal is to create an integrated ecosystem, incorporating Azure DevOps, ACR, Azure Storage, and Azure AI Foundry that solves these challenges while maintaining the efficiency of a shared infrastructure. Let's examine the governance overlay used for enforcing multi-tenant control within AKS. To ensure a secure and high-performing environment for multiple teams, we focus on three key pillars. First, we implement namespaces to provide logical separation between different lines of business, such as finance, marketing, and operations. This ensures each team's workloads remain isolated within the shared cluster. Second, we utilize resource quotas to prevent noisy neighbor issues. By setting hard limits on CPU and RAM for each namespace, we guarantee that no single team can monopolize resources at the expense of others. Finally, we employ role-based access control, or RBAC. By integrating with Entra ID groups, we ensure that developers are granted access exclusively to their assigned namespaces. This multi-layered approach provides the necessary control and security for a successful multi-tenant deployment. When we talk about effective multi-tenant governance, we look at three fundamental layers that ensure stability, security, and efficiency across different lines of business. The first layer is namespaces. Their primary function is logical separation and scoping. In practice, this means creating a dedicated namespace for each line of business, for example, BU-HR or BU-Finance, to provide a clear boundary for their respective workloads and resources. The second layer consists of resource quotas. These are vital for cost management and preventing performance degradation. By setting hard limits on CPU and memory usage for each namespace, we ensure that one line of business cannot consume excessive resources and starve another, maintaining overall system balance. Finally, we have RBAC, or Role-Based Access Control. This layer focuses on security and access management. By leveraging Entra ID groups, we can grant developers permissions that are scoped exclusively to their own namespace. This ensures that teams have the access they need to do their jobs, without compromising the security of other business units. Together, these three layers provide a robust framework for managing a shared environment. Now we arrive at the final challenge, splitting the bill. The central question we face is how to attribute costs fairly across an organization. Currently, Azure bills us for the underlying infrastructure, the virtual machine nodes themselves, rather than the logical namespaces or workloads running on top of them. As illustrated here, we have multiple lines of business, such as finance, marketing, and HR, all sharing the same VM node pool. Without a proper tool in place, it is impossible to accurately determine how much infrastructure the finance LOB consumed versus the marketing LOB. This lack of visibility creates a significant hurdle for financial accountability and resource management. Today, we are discussing a practical solution for cost allocation, the AKS Cost Analysis Add-on, powered by OpenCost. This tool provides native visibility into your expenses, broken down by standard Kubernetes constructs like namespaces. As illustrated in the chart, we can see specific cost distributions for different business units, such as finance, marketing, and HR. By leveraging this granular data, organizations can implement direct, data-driven chargeback or showback processes, ensuring financial accountability and transparency across all business units. Today, we are discussing the shared platform billing model, which provides a transparent framework for managing and allocating our cloud infrastructure expenses. This model is built on a clear, shared responsibility approach, dividing our expenditures into two primary categories. The first category is the platform tax, representing our shared costs. This includes core infrastructure components that support the entire ecosystem, such as the system node pool, load balancers, and network gateways. These are treated as platform-level operational expenses because they provide the foundation for all services, regardless of the specific business unit using them. The second category is workload costs, which are directly attributed to individual lines of business, or LOBs. Here, you can see examples like finance, marketing, and HR. These costs are billed proportionally to each LOB based on their actual resource utilization. We measure this through the specific CPU and memory consumption within their respective namespaces, using data reported by AKS Cost Analysis. To ensure comprehensive financial oversight, this granular tracking is supplemented with high-level Azure tags on the cluster, such as labeling environments for production. This dual bucket system allows us to maintain a robust platform while ensuring each department is accountable for its specific resource footprint.